open science services that are available that can help institutions to identify OA publications and data. So in our research, we selected just 3 of these services to provide data for our study: Sherpa REF, Unpaywall, and Core. And as I said, it's very interesting to see current usage at the beginning of the talk. Sherpa REF resources indicate possible OA locations from serial policies, and it's primarily used by UK institutions to support REF compliance workflows. So there's a web interface that allows you to do that. Unpaywall and Core services aggregate information on OA content and locations. For example, outputs hosted by institutional repository systems and publisher platforms. We chose these services because of the size and type of the data holdings, our confidence in the quality of the data. Unpaywall and Core are regularly used in mainstream research and information system tools. You'll also note that all these services serve a different primary function within the research landscape, and there's a range of clients, range of different means of accessing this underlying data. So they all implement a free REST API for wider consumption, and I would definitely recommend taking a look at JISC's recent blog, comparing Core to a range of other OA aggregators for a more complete summation of some services that hold data on OA. So on the back of that slide, some of you might now be asking just exactly what is a REST API. So in this section, we'll attempt to provide you with a simple summary and offer some practical examples from those open science services we used in our study. So in some ways, REST is very simple because it's using existing internet technologies and behaves in ways that we're all familiar with when we're using the web. For example, a client makes a request to a web server over HTTP. The server processes the request and responds by serving a web page, an image, or whatever it is the client has actually requested. Or if you're very unlucky, you might receive a 404 response code, meaning that the web service is down. So REST works very much in the same way. It's an architectural style that encompasses the common web standards such as HTTP, URL, HTML, and XML. And in terms of delivering web services, REST aims to ensure that these services retain the benefits of the design of the web in terms of being loosely coupled, hugely scalable, open standards based, and vendor independent technologies without introducing further complexity, constraints, or weaknesses. So really, REST is based on a re-examination of the technologies that have already made the web such a success. It's an observation that these technologies can be used directly to support web services without the need for any additional mechanisms. So it's not a standard in itself, it's not a new technology, it's a style or a different approach to implementing web services. So when RESTful web services are written, these same standards are being used to make data available for machines as well as humans. So the term was originally coined by Roy Fielding in his PhD dissertation to describe an architectural style of systems, networking, that did not require any additional mechanisms or protocols over and above existing standards. So quoting from his thesis, he described REST behavior as that of any well-designed web application, a network of web pages that provides links or state transitions that result in the next page being sent to the user. So some champion REST as a second generation approach to web services. SOAP is another quite dominant web service technology, but this is a standard that's defined by the World Wide Web Consortium. So developers that are using SOAP need to learn the details of that standard in order to implement it. So that's not the case with REST because it uses these existing technologies in order to function, and these were actually developed first alongside the internet. So XML, SOAP, and other standards are in fact later approaches. So this so-called second generation of web service is in fact simply a return to using HTTP and URIs. REST is described as stateless. Each request has to complete, carrying all the required information in order to process a request. REST uses standard HTTP operations, for example, GET, which is the request type most commonly used by your browser when retrieving web pages. REST resources are uniquely defined or identified, by URIs. Clients, software components, for example, can be used to manipulate these resources. one resource might contain URIs to other related resources. So REST is not concerned at all with how it's actually implemented. It's based really on the concept of a resource, a piece of data that's accessible anytime over a network. Each resource is defined by its own unique address and a representation that's yielded by that address. So the address of any resource in the internet is given by a URI. But it's worth bearing in mind that it's not actually necessary for any URI to actually exist as a web page. The web server, can intercept the request to a path and reply with some form of dynamic content. So just like a URL, an infinite number of URIs can be used for these purposes. And it's this dynamic handling of requests that makes it easier to support the REST model for delivering web services. The client requesting any URI receives a response that places the client in either a new or a fresh state. That's the idea behind REST providing web services. And this can be thought of in terms of the client receiving a web page that reveals a new set of links to other resources or other web pages. And from this new state, the client can select another link, and by taking that path, cross over to another page or state that reveals more links to further pages and states. The view of web services reduces the model to a very simple set of concepts: state, transition, and the transport protocol that allows the transitions to be navigated by clients. So of course, mapping this view to the internet becomes quite simple. The state is simply an HTTP response, page and content. A transition is another state that's accessible from the current state, for example, another URI available in the current state. And the underlying transport protocol is simply HTTP. So let's take this really simple example of a REST-based web service. So I've given an example here of a REST resource at example.com/lightbulb, which is just a representation of a light bulb. So the resource is uniquely located at this URI. So in this API, let's imagine that it has functions to allow a client to turn the light bulb on and off and to check the state. So if we consider that case of a light switch that wants to convey some of this information to the light, whether to be on or off. Perhaps this will give some of you a light bulb moment as well. So we could think of an on-off instruction as being a simple Boolean value, true or false, and we could use an HTTP put method to send requests to that light. So to turn the light on, for example, we could use put true to the resource. To turn the light off, we could use put false to that resource. And then to determine whether the light is on or off, we could then use a standard HTTP get method, get resource, which returns the data regarding its state, for example, whether it's true or false. So just to quickly summarize this section, REST is a stateless methodology or style transported via HTTP or HTTPS. A request is transported as a URI. Response data can be XML, JSON, or other text-based methods. An analysis of the URI and HTTP method indicate intent, which can then be processed by the server application. So let's jump straight in with a really simple real-life example with an OA web service. So Sherpa REF at the moment has quite a simple API. You pass it a resource, in this case an ISSN, and it will return some data about that resource. So I'm just going to try and change my screen now. So let's see if this works. Okay, I hope you can all see that. So this is the web page for the Sherpa REF API, and they very helpfully have a little example down here. So you have the API location, and then you have the resource, which is the ISSN at the end. So they've got an example for the publication nature. So if I enter that into the browser does a GET request, and it comes back with some data here. So this data here is in a JSON format. So it looks a bit complicated, but you have to remember that the provider is obviously has data to send you, and it's structuring it in a way that it thinks it's logical. But that can be consumed by software or a program that you develop. Okay, so let's try and go back to the presentation. Okay, I think we're back in the room. Okay, yeah, so from that, some of you might now be asking exactly what is JSON. So Again, I'll give you a very brief overview here and then some practical examples from the core service. So when considering REST, we also need to consider JSON as a lightweight data interchange format that's also been widely adopted. This is a very easy to understand text-based format that's frequently used in conjunction with REST APIs. The format is very compact, which makes it very easy for computers and people to read and write. So in terms of web applications, we can think of JSON as an alternative data interchange format to XML. In recent years, and partly because of its close links with JavaScript, JSON has become an accepted and popular alternative means to exchange data. Whilst XML is a tried and tested technology and it's already used in a huge range of applications, but JSON has advantages in that it tends to be more compact than XML, it understands JavaScript, and some would argue it's easier to read and write. But these arguments aren't quite as clear as they should be. So in any different service, if developing a web service yourself, different technologies offer different opportunities, and the reasons why one is perhaps adopted at the expense of another will often be driven by the functional requirements of that application, or it will come from the preferred skill sets and approaches of particular web service designers. But another advantage of JSON over XML is being closely based on the JavaScript notation. It's a very familiar sort of format in terms of the creation of arrays and objects particularly, which means that rather than using a parser, you can simply use standard JavaScript functions to convert JSON data into native JavaScript objects. So a good case of this is if you develop an application using HTML5, for example, this becomes quite a useful advantage. There's less work to be done. So the data maps very easily onto these data structures, which are used by most programming languages, numbers and strings, booleans, etc. And once you've created your message, your JSON message, it's easy to send it to another application or computer because it's just plain text, just like we showed there with the Sherpa REF API. So many programming languages contain functions or libraries that can read or write JSON structures. So now we'll move on to another practical example using the core service. So core, as we sort of touched on, is a huge resource holding OA data and full text for text and data mining services. And the data is accessible by the core search engine and via their API. So to use the core API, you have to register for a key, which you then pass to the service via the URI along with the request for the resource. This is just a mechanism that helps core to control usage. So it only takes a couple of seconds and just involves filling out an online form. If you're developing an application, you have to respect the API's limits, which I think is something like one request every 10 seconds. But of course, if you need something more than this, you can contact the team or use their data dumps. So let's have a look at their API documentation. And again, I'll just attempt to change the screen again. Okay, so this is the web page with the documentation for the API. So you see here they've got a whole range of operations that they've implemented for users. So you can see broadly the API accepts post and get requests. You're able to access masses of data out, by making bulk requests, or you can make queries based virtually on any data attribute held in their repository and article holdings. So we'll just quickly look at operations for retrieving articles and make a simple query using a GET request. So this gives you an overview of the structure of the data that's going to be returned. I'm just going to leave most of the values at default. There's a space at the bottom to put in your API key. So if we were to make a query for a DOI, for example, so let's first try a DOI. So we published along with our paper all the data that we retrieved from from the various web services. So we have all the core data that we retrieved. So I'll just take a DOI from there. Oops, just be able to view it. Oops. Oops. Let's see if I can get the right one. Yeah, we'll go with this one. Nope. Yeah, here we go. So with core, we actually also counted where article titles and where there were multiple locations. So this one at the top was found to have the most locations according to core, 9 locations. So I'll just look it up very quickly to get the DOI. Okay, so this is the paper. Here's the DOI. Oops. And I'll just put that into the API. It just comes back. Query bit, you put in the DOI. Oops. Give it a try. And there you go. So you can see it's come back with 3 hits, three records from core, and all this data as well. So as I was saying, you can search by any parameter. So you can try again searching by title. We tried both approaches actually in our study. Having a unique identifier like a DOI obviously has its advantages though. So searching by title, oh, not found, that's not good. Ah, that's right, DOI, so change that to title. Here we go, so you can see it's come back with a number of hits, more hits going by article title. So obviously that's quite a lot of data. And obviously each URI is implemented differently. Their data structures for their data are going to be different. I find it quite helpful to use things like a JSON viewer. Oops. Like this one I use quite regularly. This is quite good. You can just paste the data that you've got if you just want to have a look at what the structure is. And you can see here you've got the JSON object and the number of hits and the data in an array here. You can see we've had 9 records returned. So let's just go through some of these. So the first record, title matches, improving the experience of dementia. This was found in LSE Research Online. Let's have a look at the second one. Second one, same paper, found in Sussex Research. And let's have a look at this one here. This one was found, the same paper again, found in King's Research Portal. So these results are obviously highly interesting, especially when you think of it in context of the collaborative OA activity that Chris was talking about earlier, especially when you're considering how institutions are requiring authors now to work towards open access. If you try looking for these papers in Google Scholar as well, you see another interesting difference that comes back. I won't do it now, but earlier we did a little scan for this paper, and we found 23 versions in Google Scholar. Obviously, these tools are really good, but they are more limited than Google's All-Seeing Eye. Okay, so I'll just return now to the presentation. This one. Ah. Oh, hi, Maria.
Yeah, hi.
Sorry.
I can still see the JSON viewer at the moment. Maybe try hitting the blue flower in the start bar to get you back to the right place.
Ah.
Yeah. Now do it.
Here we go. Sorry, we're back on track now.
Yeah, perfect. I can see the slides.
There we go. Yeah, we're back. Okay, great. Right, let's move on. Okay, yeah. So in our research, we actually found that core found some 1,800 locations for just over 1,000 publications. We found 370 distinct works found in multiple OA locations, so that's just over a third of papers from that sample. if you follow that link, which I've listed on the slides, you can also see a map. We plotted all those locations. It's quite impressive to see. You can see the results form really a collaborative picture that begins to emerge once institutions have access to this type of data. OA networks are spread collaboratively, and they intersect with individual researchers and institutions. So we're beginning to think from our results that there may be a tension indicated between that implementation of OA policies at a local level and the collaborative research enterprise. So in this last section, I'll touch on Unpaywall and their research into global OA levels. So this is the final service on our list, Unpaywall. They recently published a hugely insightful paper onto global levels of OA by published works with DOIs, and this paper was titled The State of OA. Quite correctly, they initially define OA at a very high level. OA is free to read online, either on the publisher website or in an OA repository. And all articles not meeting this definition were defined as closed. They found some 45% of recent works being made available as OA, and this is a very useful global benchmark. But nonetheless, they do classify several OA subtypes, of which the most common type found was bronze OA. This was actually a new type which they coined themselves. So bronze OA is a form of publisher OA. When the work is open access, copyrights are held by the publisher. So in our paper, we distinguish between types of closed works, those closed by the publisher through a lack of an archival policy, and those closed by the author, where an archival option exists but is yet to be taken up. And we'll talk about why that is in just a few slides. So Unpaywall also have an API and client services for monitoring OA. Institutions really should make good use of it. It's very, very fast. And I think you can make something like 10,000 requests a day. So lots of data that could be coming your way. Unpaywall is fast becoming the best source of identifying OA information for a publication. It's very easy to use and the data is very robust. Their API is free to use and it operates on exactly the same principles as those that we've just discussed. So now we move on to our last section, which is the results of our research that we published in the journal Publications early this year. So this formed part of a special issue on open access put together by the British Library. So these were loosely the aims of the project, and we've already touched on some of these already. We wanted to create an OA classification schemes to interpret our data. So we largely built upon the work by Unpaywall here, but with some differences as I just discussed. We wanted to investigate possible OA locations, and for that we decided to use Sherpa REF. We also wanted to investigate OA locations and plot the geolocation of Brunel works. We discussed this earlier on. And we wanted to investigate OA locations and volume, particularly using Unpaywall. So in our research, we liken this approach to the metaphor of a telescope, looking outward from our institution to systems beyond, which form a collaborative OA universe. So getting into it now, our results show a multitude of OA locations and activity brought about through research collaboration that intersect with our institution. The key finding from the Sherpa REF data was that there were 34 total OA scenarios for authors. And if you follow the link on this slide, you can have a look at our data. So a significant number of titles adapt to 8 possible OA scenarios. And we think what this shows is the scale of possible OA locations available to authors when making dissemination decisions for their research. So this example that we cite in the paper is the OA dissemination options for the Journal of Applied Physics. So as you can see here, it has up to 13 open access scenarios, and not counting when you have multiple authors possibly considering different OA routes. So the complexities and range of publisher policies combined with funder and institutional policies may create opportunities for duplication in OA locations. So I'll just touch on our discoveries for OA volume at Brunel that we found using these services. So this shows total journal articles and conference papers over the last 4 years or so. The orange colours are gold and hybrid OA. The green colours are institutional and subject repositories, and the purple and black are variants of closed access. So with a complete global record of our activity, this means our institutional services can now effectively target researchers. Our role is to provide advocacy and support. Researchers with a green OA option can be guided towards repositories. So this is shown here in this figure, the closed access works, the purple band. So for Brunel, this amounted to just 7% of papers in 2016. And that's quite important when you consider that the teams that are supporting this work are usually quite small and need to target their resources quite strategically. It also provides a spotlight on those publishers without archival policies, again, which is quite useful in terms of supporting advocacy work. And that's something that I don't really hear enough about, I think, is publishers that aren't providing these mechanisms to make their authors allow them to make their work open access. So we've seen growth at Brunel in terms of hybrid and green, which again reflects the policy landscape somewhat. But we haven't seen as much growth in the adoption of gold OA journals. This is a trend identified in UUK's report. Gold OA journals only account for about 10% of the market overall. That's worth bearing in mind, I think. And just to end this section, I'll touch on our results which is the theme of our presentation in terms of the replication and multiplicity of OA works for Brunel. So in our sample, we found that most gold works are found in other locations irrespective of the publishing license. So we found about 30% of gold and hybrid works were available under a bronze model. So this graph here shows that green is, without a doubt, the most popular form of OA at our institution, but it's quite interesting to note that it doesn't really have very much replication. This is a sort of variant of that graph, average OA locations. Gold and hybrid, on the other hand, do have a lot of replication. So on average, gold is replicated in 3 locations, hybrid is replicated at least twice. Again, some interesting findings, but I'll finish it off there and just hand back over to Chris for